we are discussing the concept of derivative with the help of seconds of a curve. So let us this is a reference point for a particle which is moving, and its displacement at time t from this reference point is given by a function that is, this is displacement of particle from this reference point at t1, let it is t1, at t2 this displacement is, at t1 displacement is d1, at t2 displacement is d2. Similarly at t3, t4 you can find the displacement of particle from r. So this displacement is denoted by st, is a function of time, and the function is st is equal to t square. So let us just draw this function. You know, this is simple parabolic function. This is simple parabolic function. As time cannot be negative in classical physics, we know, so we will eliminate this section of the curve because we are talking about real time. So this is the curve which gives displacement of particle from its reference point at t1, t2, at point t1, t2, t3, t4, etc. So this is parabolic curve. This equation gives distance from reference point for a particle at different time intervals, at different points. So let us take t is equal to 1. T is equal to 1. T is equal to different time intervals. We will have different time intervals. T is equal to 4. T is equal to 3, T is equal to 2, T is equal to 1.5, and T is equal to 1. These are the different time intervals. At 1, its displacement is given by this length. At 1.5, displacement is given by this length. At time t equal to 2, the displacement from this reference point is given by this length. Time t equal to 3, displacement is given by this, and time t equal to 4, its displacement is given by this. So at time t equal to 1, put t equal to 1, you will find, let this displacement is given in terms of meter and time is given in terms of second. T equal to 1, displacement is 1. T is equal to 2, displacement is 4. T is equal to 3, displacement is 9. T is equal to 4, displacement is 16. And T is equal to 1.5, displacement is 2.25. So this is displacement at different time intervals. what we will do, we will take time interval from t equal to 1 to t 1.5, from 1 to t equal to 2, that is 2 seconds, from 1 to t equal to 3, that is 2 seconds, 1 to 4, that is 3 seconds. These are the different time intervals. So we know the formula for average velocity. V average is displacement divided by time. V average velocity for time interval t is displacement covered in time interval t, that is delta s by delta t, for any 2 points. We all know this simple formula. So based on this formula, you can find average velocity between, let V14, that is average velocity between time t equal to 1 to t equal to 4. This will be displacement at 4, 16, and 1 is 19, that is delta s, displacement covered from time t equal to 1 to time t equal to 4 is this, and time interval is 4 minus 1 is equal to 15 by 3 is 5 meter per second. So the average velocity between t equal to 1 to 4 is 5 meter per second. So geometrically, just make this less congested. Geometrically, you can join these 2 points. T equal to 1 point is this, t equal to 4 point is this. So join these 2 points by a secant. By this secant. Now this is a line. This is a line. And we know the definition of gradient of a line. What is gradient of a line? For a given line, that this is x-axis and it makes angle theta, the gradient m is defined as vertical height covered with unit horizontal distance. That is, let this distance is y, this distance is x. So when we reaches at this point, so vertical height covered is y and horizontal distance is x. So vertical height per unit horizontal distance is y by x. Y by x. This is vertical height per unit distance. And by definition from simple trigonometry, you can see this is tan theta. So this is called gradient of a line. Definition of gradient. For any slope also, any slope, you can find gradient of slope is when you go along the slope, you will move vertical as well as horizontal. So vertical distance covered per unit horizontal distance is the slope. That is y by x. Vertical distance covered per unit horizontal distance is y by x, that is tan theta. So this is also called gradient of line. So this is a second joining point t equal to 1 to t equal to 4 of this graph. So if you will find the gradient of this line is also vertical distance is divided by horizontal distance. Horizontal distance is 4 minus 1 and vertical distance is 16 minus 1. So that is also 5. So you can see the average velocity is equal to gradient of this secant joining point t equal to 1 to t equal to 4. Average velocity is equal to gradient. Similarly, take another second. Joining point t is equal to 1 and t is equal to 2. T is equal to 3. Sorry. We will keep one constant for all. T equal to 1 constant for all. So average velocity for t is equal to 1 to t is equal to 3. Average velocity of particle between time interval t equal to 1 to t equal to 3 is distance covered in this time interval. That is, t equal to 3, its displacement is 9. At t equal to 1, its displacement is 1. So displacement between 1 to 3 is 9 minus 1, and time interval delta t 3 minus 1, that is 2. So this will come 8 by 2, that is 4 meter per second. Similarly, if you find the gradient of this second joining point t equal to 1 to t equal to 3, the gradient will also be 9 minus 1 by 3 minus 1 equal to 2. Vertical distance, that is 9 minus 1. So this is vertical distance. This is vertical distance, 9 minus 1. Similarly, this was vertical distance, 16 minus 1. This is 9 minus 1. And horizontal distance, 1 to 3 is 2. So gradient of this second joining point t1 to t equal to 3 is also same with average velocity between t equal to 1 to t equal to 3. Similarly, same exercise we will conduct for t equal to 1 to 2. Average velocity is 1 to 2, that is 4 minus 1 divided by 1, that is 3 meter per second. And gradient m for second joining point t equal to 1 and 2 is also 4 minus 1 by 1 equal to 3. Similarly, for t equal to 1 to t equal to 1.5, t equal to 1 to t equal to 1.5, V average is 2.25 minus 1 divided by 0.5. Time interval is 0.5. So this formula we are using for average velocity. So you will get 1.25 by 0.5 is equal to 2.5 meter per second. Similarly, you will find the joining second of 1 t equal to 1 to t equal to 1.5. You will find gradient equal to 2.5. So, what is our observation during this exercise? You will make a table and observe. You will make a table and observe the relation between average velocity, gradient of seconds, and then we will see how this gradient of second is converted into gradient of tangent as we approaches from 4 to 1. So we are approaching from point this 4, 3 to 1.5. So as we are approaching to 1, we are seeing that average velocity is also approaching to a certain value. So let us draw the table. T equal to 1. T equal to 1, and this is 1, 1, 1, 1. Second, and the second point t is equal to 4, 4, 3, 2 and 1.5. So you can see this point is fixed, t equal to 1, and this point is t equal to 4, t equal to 3, t equal to 2, t is equal to 1.5. Find the delta t. Delta t. Delta t for this interval is 3, for this interval is 2, for this interval is 1, for this interval is 0.5. Now find delta s. Delta s, displacement in this time t. So delta s will be s t minus s1. You can put t equal to 2, t equal to 3. So you will find delta s of that interval. So for t is equal to 4, delta s is 4 square minus 1 square is equal to 15. Delta s is st minus s. For a particular value of time, delta s between t equal to 1 to t equal to t is given by this. Or you can say, let for t displacement is st, and for t is equal to t plus delta t, displacement is s t plus delta t. So delta s is equal to s t plus delta t minus st. In terms of delta t, you can find displacement from this, or same thing you can find from this between t equal to 1 to t equal to any instant of time. You can find delta s. From this also you can find, you can put t equal to 1 s1, and for any particular value of time you can find delta s. So delta s between t equal to 1 to t equal to 4, delta t is t and delta s is this. Similarly, for t equal to 3, delta s will be st, that is 3 square minus 1 square is equal to 8. For delta t is equal to t equal to 4, delta s is 2 square minus 1 square is equal to 3. Similarly, for this, delta t is equal to 1, delta s equal to 1.5 square minus 1 square, 1.25. That is delta s. Now you find m, gradient of second joining these points, or average velocity v average is equal to delta s by delta t. So for this time interval, delta s by delta t is 15 by 3 is 5. For this time interval, delta t is 2, delta s is 8, 8 by 2 is equal to 4. For this time interval, delta s is 3 and this is 2, so this is 3 by delta t is 1, sorry. So this is average velocity is 3. And for this time interval, t equal to 1 to t equal to 1.5, delta t is 0.5, delta s is 1.25, delta t is 0.5, and this is equal to 2.5. So in this table you can see, as this we are finding average velocity for points closer to original point, that is t equal to 1. The average velocity or gradient of seconds which are same are also changing, and changing from 5 to 4 to 3 to 2.5. That is, for t equal to 1 to t equal to 1.5, average velocity is 2.5. So till here we have seen that, the average velocity when we are approaching from t equal to 4 to t equal to 3 to t equal to 2 to t equal to 1.5. So when we are reducing the delta t, so we know the average velocity is approaching more and more closer to instantaneous velocity at t equal to 1. So what is instantaneous velocity? We know velocity at every point of time is changing. At every point of time, velocity is changing, no matter how small time interval is. Delta t can be 0.0001 second. Still, velocity will change within this small time interval also. So at every time there is particular velocity associated with that time. So we will have instantaneous velocity at every time. T equal to 1, we will have some instantaneous velocity. T equal to 1.5, we will have different instantaneous velocity. T equal to 2, we will have other instantaneous velocity. So for every point of time, we will have fixed instantaneous velocity at that particular point of time. So instantaneous velocity, what will be instantaneous velocity? Instantaneous velocity, so let us find instantaneous velocity at t equal to 1. V instantaneous at t is equal to 1. So you can see, when we find average velocity between 2 points, when those points will be closer, more and more closer, the average velocity will be more corrected with instantaneous velocity. The average velocity will match with instantaneous velocity when those both points of average velocity merge with each other. When this point come closer and closer and merge with this point, then average velocity between those 2 points will be instantaneous velocity at t equal to 1. So let us find instantaneous velocity at t is equal to 1. So we have st is equal to t square. We can always find average velocity between any 2 points. So here you are seeing that as the delta t is decreasing, the velocity, average velocity is also approaching to certain value. And when delta t will be 0, what you will get? You will get instantaneous velocity at t equal to 1. When this delta t is between time, instantaneous time, and t equal to 1. So when these both points will merge with t equal to 1, you will find instantaneous velocity. As t is t square. So let at time t equal to 1, at t is equal to 1, displacement is 1 square is equal to 1. Let us increase time by very small fraction. T is equal to 1 plus delta t. T1 is 1 and T2 is 1 plus delta t. Delta t is very small time interval. T is equal to 1 and 1 plus delta t is like very close to this point, t equal to 1. So now at T2 is equal to t plus delta t, displacement will be as 1 plus delta t is equal to 1 plus delta t square is equal to 1 plus delta t square plus 2 into 1 into delta t. That is displacement at 1 plus delta t time. Displacement at time t equal to 1 is 1. So delta s, displacement covered in delta t, displacement covered in delta t time will be s1 plus delta t minus s1. That is displacement of particle in this time interval will be s1 plus delta t minus s1 from t equal to 1. So delta s is equal to s1 plus delta t is this 1 plus delta t square plus 2 delta t minus 1. S1 is 1. So this is equal to delta t square plus 2 into delta t. Delta s is this. So displacement covered by particle between t equal to 1 to t equal to t plus delta t, that is in delta t time interval, is this. So average velocity V average for time interval delta t is delta s by delta t is equal to delta s is this delta t square plus 2 into delta t divided by delta t, and this is equal to 2 plus delta t. So we found average velocity. So this average velocity is also gradient of second joining point t equal to 1 and t equal to 1 plus delta t. This will be gradient of second, and this is also average velocity for time interval delta t from t equal to 1. So now we will find instantaneous velocity. How will we find instantaneous velocity? We know V average is equal to delta s by delta t. No matter how small delta t is, this will always be V average. We will use the concept of limit V instantaneous at t is equal to 1 is equal to limit delta t is tending to 0, delta s by delta t. So we will find ratio, value of this ratio, which is average velocity for delta t time interval. So when delta t will be 0, then this point will come more and more close to t equal to 1. And when delta t will be 0, it will merge with t equal to 1. So we will find the ratio, this average velocity will convert in instantaneous velocity at t is equal to 1. So delta s by delta t is 2 plus delta t, that is limit delta t is tending to 0, 2 plus delta t is equal to 2. So V instantaneous at t is equal to 1. So we have found V instantaneous at t is equal to 1 equal to 2. So here also you can see this value 5, 4, 3, 2.5. These values were approaching to 2 when we were approaching from t equal to 4 to t equal to 1. So these all average velocities were approaching to 2 instantaneous velocity at time t equal to 1. So you can say these average velocities were gradient of seconds for corresponding points. Similarly, this instantaneous velocity is also equal to gradient of a line, and that line is called tangent. So instantaneous velocity at t is equal to 1 this is t is equal to 1. So instantaneous value is also equal to a line which is called tangent. This is tangent. Tangent at t equal to 1 of this curve st equal to t square will be, the gradient of tangent will be equal to instantaneous velocity of particle at t is equal to 1, just analogous to the second's gradient. Gradient of second was equal to average velocity of particle between the two joining points, corresponding points. Similarly, gradient of tangent at a particular value is also equal to instantaneous value of that at that time. So this is the way we find instantaneous value, and we define derivatives. Derivative, I will define derivative precisely how it is defined actually. You have just got the idea how derivatives are related with instantaneous change of rate of change. So similarly, a function is given. Derivative of this function is defined as dy over dx. Why dy over dx? And this derivative is defined at limit, in terms of limit x is tending to a for a particular value. Derivatives are always defined at a particular value. You just remember, as in earlier case we have found derivative at t is equal to 1, that was equal to 2. It is always at a particular value of x, and general value, general expression you can also find for derivative, but derivatives are meaningful only for a particular value when you are talking about physical quantities like velocity, accelerations. So at value x equal to a, differentiation derivative is defined f a plus delta x minus f a divided by delta x. This you can also write as limit x is tending to a delta y by delta x. So this term is delta y and this term is delta x. This whole term is delta y when value of a x, as x equal to a, function is f a. At x equal to a plus delta x, function value is f a plus delta x. So when you will subtract from this to this, you will find delta y. So this limit you can write like this also. You will say delta x is tending to 0. You write like this, not x. So the derivative is defined when this small increment is tending to 0. In that case, ratio of changes in function value and in the value of dependent variable. So you can write like this also. So what is derivative? This is written as f dash x also. This is written as dy over dx also. So this dy over dx notation was given by Leibniz. This is called Leibnizian notation. And this f dash x notation was proposed by Lagrange based on Newton's theory of fluxes. Newton and Leibniz separately discovered calculus. So they proposed their own nomenclature. So this is Lagrangian nomenclature based on Newton's calculus, and this is Leibniz notation based on calculus developed by Leibniz. Both are same. This is defined as ratios, changes in function and changes in dependent variable when this increment is tending to 0. So this is a instantaneous ratio of changes for a value of function and changes in value of dependent. So this derivative is nothing but ratio of infinitely small changes. Infinitely small changes ratio is derivative. So practically when you will find delta y by delta x, so this value you will put some real value delta y and real value delta x. This will be more and more closer to this limiting value, but not exactly equal to this limiting value. As we were finding average velocities, and average velocity was coming to instantaneous velocity when we were changing from t equal to 4 to t equal to 3, t equal to 1.5, t equal to 1. That velocity was merging to 2. Similarly, this delta y over delta x is average ratio of changes, just like average velocity and average velocity. So that was not equal to instantaneous velocity, and this is instantaneous rate of changes, instantaneous ratio of changes, that is limiting ratio of changes, whatever you want to say. This is limiting ratio of changes in y and x. Changes delta y and delta x, delta y and delta x. Okay. So this is the way to find the value of derivative. So in that case, you can find general expression for instantaneous velocity. In that case, displacement was function of time t square. Displacement was a function of time t square. So let us find a general value of velocity, instantaneous velocity. So let there is particular time t. So for time t plus delta t, displacement will be s t plus delta t. So from t to delta t, delta s is equal to s t plus delta t minus s t is equal to t plus delta t square minus t square is equal to t square plus delta t square plus 2t delta t minus t square. This is delta t square plus 2t delta t. So this is displacement, or you can say it is a function, change in function when value of dependent variable or time change from t to delta t. For this delta t change, you find delta s equal to this. Find the ratio of delta s by delta t. That is 2t plus delta t. So when you will put finite values of delta t, finite values of delta t, that is 0.1, 0.2, 0.3, you will find this ratio. So you can see, so let us just complete it. Instantaneous velocity v instantaneous is equal to limit delta t is tending to 0, delta s by delta t is equal to 2t plus delta t. Put the value of delta t 0, it will come 2t. So we can write ds over dt is equal to s dash t in Newtonian form is equal to 2t. So derivative of displacement with respect to time is instantaneous velocity at time t. This is general expression. In our earlier example, put t is equal to 1. We have found average velocity, instantaneous velocity at t is equal to 1. T is equal to 1, you will get ds over dt or v instantaneous is equal to 2 into 1. So here you can see you can put any value of time. T equal to 2, at t is equal to 1, instantaneous velocity is 2. At t is equal to 2, v instantaneous is equal to 4. At t is equal to 3, v instantaneous is equal to 6. So like that. So you can find a general expression of differentiation derivative. In that general expression also you can put different value of dependent variable to find instantaneous rate of small changes. Instantaneous rate of small changes. So that change can be any other quantity. Here that change, that ratio is V instantaneous. So these are different values of time. Sorry, in derivative. So again, just remember delta y over delta x is approximately equal to dy over dx, because these are finite small values. Here delta x is equal to not 0, but in this case delta x is equal to 0. Delta y over delta x, no matter how small they are, but delta x has certain finite value, let's say 0.0000. But when we find delta y over delta x at certain point, at that point delta x is 0. That is the definition of dy over dx. Delta x is tending to almost 0. It is 0, exactly 0. So this value is exact value of ratio of delta y over delta x when delta x is 0, instantaneous ratio. But this value is not instantaneous but average value over the period delta x, over the span delta x. So this is always approximately equal to 0. Please remember, approximately. This concept is asked in many examinations to find the error, to calculate the error in measurement, error in calculation. This method is used. Dy over dx is exact ratio, delta y over delta x is approximate ratio. Just please remember. So now we will also discuss some derivative of some properties of derivative. Just look at a glance. There is a function fx. So derivative of addition of two functions is given by, in Newtonian form you can write it f dash x is equal to derivative of this function plus derivative of this function. In Leibniz form you can say ddx of fx is equal to ddx of fx plus ddx of gx. So this is the property of addition of two functions, how the derivative of two functions which are being added is found. This is one property of function. Similarly for minus, you can just change the sign. This is one property of derivative. Second property is multiplication property, that is fx is equal to fx into gx. So f dash x, derivative of this multiplication will be f dash x gx plus g dash x. This is in Newtonian form, Lagrangian representation. Similarly, by ddx you can represent in terms of Leibniz form. Third property is for dividing the function. For division, there is rule of differentiation. Let fx is equal to fx divided by gx. Then f dash x equal to gx f dash x minus fx g dash x divided by gx square. This is rule of division. You can write another third rule we forgot, that is composition. Let fx is equal to f of gx. That is called chain rule. Chain rule. It is so. Let y is equal to fu and u is equal to suppose gx. So we can write the function of dy over dx is equal to f dash u, or you can say directly in Leibniz notation. Let us write completely in Leibniz notation. ddu of fu into du over dx. When there are two functions, this is the composite function. In case of composite functions, what is this? This function is a composite function of, there is a function, composite function of f and u. F and u. When there are composite function inside a function, in that case you can use the chain rule, dy over dx, ddu of fu into du over dx. So this is the method to find the differentiation of a composite function. This is called chain rule. You can remember it by just because it cannot be divided. This is not division. Just remember, dy over dx is not division. This is just representation. You cannot cut it, but for remembering purpose, you can remember it like this. So this is chain rule for composite functions. So let us find derivative of implicit function. We have defined implicit function as function where dependent and independent variable are arranged in its common expression. So here you have to find dy over dx. So how will you find it? There are two methods. First of all, you find y is equal to plus minus under root a square minus x square. Find dy over dx, assuming first case assuming plus, second case assuming negative. So with this method also you can find, both will come same, but for complex function this method will be very difficult to solve. So second method is, let us differentiate both sides with respect to x. ddx of x square plus ddx of y square is equal to 0. That is constant. This is 2x plus, from chain rule you can write it dy of y square into dy over dx. This is chain rule is equal to 0. 2x plus 2 by dy over dx is equal to 0. So here you can say dy over dx is equal to minus x by y. Dy over dx is minus x by y. So you can write it like this, or from this, just for example, take positive sign under root a square minus x square. Differentiate dy over dx is equal to, so you can write it half a square minus x square power minus 1 by 2 into minus 2x. By differentiating it, you can write it like this: minus x divided by under root a square minus x square. And a square minus x square is y. That is minus x y. So here also, similarly with negative sign, you will also get same. You will get same expression. So in case of implicit function, this technique is simple, which you can use to find derivative instead of making it an explicit function and then finding derivative. So derivative is nothing but, in terms of Newton or Leibniz, but whoever have proposed this concept of derivative, this is the ratio of increments. In simple language, derivative is ratio of increments, infinitely small increments. This is also by Newton it was called ultimate ratio. Newton called it ultimate ratio. Ultimate ratio, and Leibniz explained it with the help of tangent. The gradient of tangent is equal to derivative of the function at point of contact. So Leibniz defined derivative by the gradient of tangent, and Newton defined the derivative as a infinite ratio of infinitely small changes in dependent variable and independent variable, and he called this ratio as ultimate ratio. Newton called this ratio as ultimate ratio. It was nascent increments, ratio of nascent increments, very small increment, because during the age of Newton and Leibniz, the concept of limit was not existing, which we have used here, the concept of limit. But they have by intuition, they have feeling that as these increments are approaching to 0, their ratio of increment is also approaching to certain value. That feeling they had, but they could not properly define it because limiting concept of limit was not available at the time of Newton and Leibniz. So a derivative is nothing but it is a limiting ratio. It is a ratio of infinitely small changes in dependent variable and independent variable. At a certain value of dependent variable, you will find this ratio different. So we have find at t equal to 1, 2, 3 different instantaneous velocities. Similarly, you can say at different value of dependent variable, this ratio of small changes will also be different.